Thank you to everyone for joining us today's webinar, Asset Integrity in the Digital Age. I think basically we're going to talk about how we've created a partnership between ourselves and Abyss Solutions that brings together their cutting-edge vision systems and laser scanning technology, along with Element Singapore's inspection, materials testing capability, and the Element Digital Engineering team in Cambridge who do advanced structural analysis and simulation and fitness for service. We believe this delivers a modern approach to asset integrity that's faster, cheaper and less disruptive to the operations of these high value assets. Before we get started, I thought we'd better do a little bit of an introduction about ourselves. Abyss Solutions are famous for artificial intelligence, machine learning and robotic systems. They've seen significant growth in the last 10 years or so, especially around the energy sector, and they've got some impressive clients that they've been working with in that period. There are some notes there on the slide about their approach, and I don't really want to give too much away or steal too much of Hamza's thunder, but just quickly summarising it. Their approach is to gather point cloud data, laser scanning, combine that with images and use artificial intelligence to identify areas where you may get damage from various mechanisms, including corrosion. That allows us to then quickly pinpoint areas of concern on a plant, and the team and Element can get to work on that fitness for service assessment. So that's a little bit about Abyss. Element, humongous company these days. Again, over the last 10 or 15 years, it's seen significant growth. We're in over 30 countries. I think this slide's a little bit out of date already. We've got over 270 locations and we're getting close to 10,000 people now. I could spend all day talking about Element and all the intricacies of the testing, inspection, certification services that we provide. But I think just really, our customers like us. The NPS score, which is a net promoter score at plus 65, shows that our customers will promote us and will advise people to use us and will come back. So positive things from our customers, which is great, from our customer focus. And again, colleague engagement score. People like working at Element. A score of 75% is remarkable. We keep working on that and we keep improving that year on year. So the representatives today from Element are Element Singapore Laboratory and Element Cambridge in the UK on the digital engineering team. So just to go through or summarise what we're going to be talking about today, I'll kick off and talk a little bit about what asset integrity is to us and why we think it's important. Talk a little bit more about the partnership with Abyss and introduce the speakers. And I think at that point, it's over to the speakers to take us through a case study. I think a case study is quite a good way of communicating how these things are actually applied in a real life situation. And the case study we've got today is looking at corrosion under pipework support. Quite a common problem across the oil and gas sector and the energy sector and the chemical and process sectors. So hopefully that's going to be of interest to everybody who's online today. I'll let the speakers take you through some of the detail on that, and when they're finished, I'll wrap up with a bit of a summary, and then we'll get into a question and answer session at the end. Hopefully, we're reasonably time limited. Hopefully, we'll have time to get through all of that today. If we don't get to all the questions, then personal promise from me, we will get in touch after the session and answer any questions that are left. Just to get started, then. What is integrity management? There's three definitions there. One from the Welding Institute, the American Institute of Chemical Engineers, the Institute of Asset Management. It's a huge area, and there are lots of different ways of thinking about this. But I think for us, and for myself in particular, large organisations who own and operate expensive assets want to extract the most value that they can from those assets with the least cost and the least disruption to their operation. And I think the solution that we've got today will help with that. Why is it important to do it? Well, there's lots of legislation out there that tells you you must do it in order that you can keep operating safely. And there's lots of guidance that will help you to try and do that efficiently. Oops, sorry, I've clicked the wrong button there. I think for me, doing asset integrity management in a systematic and organised way allows an organisation a level of control when things change. And a good example of that is when there's a price shift in the market and an organisation wants to shift their operation to respond to that price shift. Having an organised and systematic asset integrity management approach allows you to understand the future condition of your plant when those changes are made, and that in turn allows you to plan for the future better. The problem with integrity management is that it can be quite expensive, it can be time consuming, and it can be quite disruptive to an organisation's operations. And I think therein lies the problem, and therein lies the basis of today's presentation, really. I think we've come up with a novel approach that allows us to combine some advanced inspection techniques with some really world-class leading solutions in terms of materials and inspection and modelling and simulation and fitness for service assessments. So a little bit more on the partnership. We're combined with Abyss Solutions, Element Singapore, and Element Digital Engineering in Cambridge to work in partnership across the life cycle to deliver that solution. And that's a bit of a sales pitch. I'll stop talking about that really, and we'll get to the case study, which, as mentioned, it's a particular issue that I hope is of interest to the audience. It's corrosion of the pipework support. And this graphic really just shows the process that we go through from a very high level before we get into the presentations from each of the presenters. The image on the left there comes from Abyss Solutions. You can see a typical image of a pipework support with some highlighted area of damage, which may or may not be an area of concern. But what that tells us is go and have a look at that area. So the team from Singapore were able to get in there and do some replication work, and from that we're able to identify various materials tests that needed to be done in order to support the fitness for service assessment. All of that information, the point cloud data, the geometry, the replication, the chemical data, etc., that was all sent to the guys in Cambridge, who were then able to very quickly and effectively put together a very bespoke finite element analysis and structural analysis that then supported a fitness for service assessment. And it's a really efficient, really fast process that I'm really confident with, and I think it will transform the way that these things are done. So over to the speakers. First up will be Hamza Alam, who's based out in Abyss's operations in the Middle East, Asia Pacific. Abyss is an operations manager in the Middle East. He'll be talking about what Abyss have done to quickly inspect this plant. He'll then hand over to Basab, who basically is a technical lead in our energy operations out in the Element Singapore laboratory. And Rob Kulka will come up last. He'll use the information that those guys have gathered to show you how we can put that together for a structural assessment that gets into fitness for service assessment. So I think it's over to you, Hamza, when you're ready.
Yep. Thanks, John. So yeah, we'll quickly go through what we were given by one of our customers and the problem that we were trying to solve. But before that, how the process actually works for us is a very simple three-stage mechanism where we use some advanced laser scanning devices to collect data from the facility. This data comes to us in the form of laser scan and high definition imagery. And we convert that data to a usable format before putting into the processing stage, where we utilize our artificial intelligence algorithms to understand defects, detect them, classify them, and quantify them using the technology, all of which is done through the software automatically. Once that's done, we go to the third stage, which is delivery of the insights. So according to the specific criteria defined by the regulatory authority in the region or the defined criteria by the user, we create automated inspection reports, which can then go into the series of processes that we're gonna see in the next few stages as well. So this is like a high level overview of the process. In the next slide, what we did was once we applied this three-stage process to one of the offshore facilities in question here, one of the problems that we were given at the very start of the project was that there are instances of corrosion under pipe supports all across the facility. It's a huge facility, and it's becoming very difficult to manage, track, and even investigate these instances. So when we applied the system and we used the AI algorithms to segment the data and detect the damage, we were able to get quite a few of these instances as part of the output of our system. So the what we did on top of that was we used our classification mechanism to further segment out of all of these cups instances which ones need to be taken to a higher priority in terms of severity of damage and in terms of the consequence of failure associated with that type of equipment. So if it's, let's say, a process equipment or a process gas line, it would take a higher priority with respect to, let's say, an instrument circuit or instrument ear type of circuit. So that's what we did. We got quite a few insights, and using those insights, we were able to narrow down into one of the highest priority instances that was then identified as a 4-inch hydrocarbon service line with a high priority cups instance, as you can see on the right hand side. We were able to detect it, classify it, and deliver it to the end user, who then confirmed that this is definitely the type of thing that they have been having issues with. So immediately that led to a trigger in the operational um, delivery of a detailed investigation using this input, and then this entire stream of data was handed over to the element team in order to do a detailed investigation at that point. So this is how we kind of visualize what the output looks like in a 3D and a 2D format, so that the element uh, team can remotely access this data. They were able to understand what are the requirements for a site investigation. And at the end, I think Rob will comment on how this data actually impacted their assessments at the end of data collection, which was more of a finite element type of assessment. So we lumped everything together and transferred it over to the element guys to kind of take it from there. So I think it's over to you, Basab. Oh, yeah, a quick one on some of the quantified outputs. So as you can see in the previous slides, we were able to detect and classify the damage, but once we had identified a high priority item, we were able to go a bit further and analyze the data remotely through our system to quantify that damage. How much of a corrosion product buildup do we see? What kind of pitting are we seeing, and what is that? What is the exact quantity of that damage within that data? Because we're using laser point cloud inputs, we were able to extract this very easily and transfer it over to the team at Element for their detailed assessment. So I believe now it's over to Vasab.
Thank you, Hamza, and thanks for presenting this high-end inspection incorporating AI technology, which enable us to locate critical locations much faster. After identifying this location, it was our responsibility as a testing lab to confirm the severity of this pollution. And when necessary, we requested to extract sample from this location for lab-based analysis. This slide, we will elaborate the investigation method whereby we found out the damage mechanism. Our investigation started as usual with visual inspection, followed by standard conventional NDT. And we have done, upon approval, we have taken some sample for in-house lab analysis, and a comprehensive report was supplied to client. Purpose was to determine the condition of the asset and assess the type of damage. So in the next slide, we will show the damages or corrosion we have found in the pipe. The inspection revealed corrosion damage which some area exhibited pits. The corrosion was most pronounced under the insulation, as Abbas team has correctly identified, and it is due to the exposure to seawater. Visual investigation indicated the corrosion is primary at the surface level with no signs of extensive internal damage. However, we needed to do some further analysis, and hence the sample was sent to lab for analysis. Seawater exposure is obvious, and it's due to the sea condition of the asset. Inspection finding highlighted the importance of adequate protective measures such as coating or catalytic protection in marine environment. We needed to do further investigation to find the extent of severity. Before that, we will talk about some NDT inspection. We have done thorough conventional NDT, and we found mainly surface damage. In some area, we also found some indication through the thickness by PAUD measurement. The initial observation, visual and NDT suggested that corrosion is primarily caused due to the exposure to seawater. The corrosion is accelerated due to moist environment. On-site laboratory, inside the in-lab testing of the material was done. We first started with replica work at the site. There was no anomaly found. Occasionally, we found some large grain. We have taken hardness. There was no issue with the hardness. So, in summary, we haven't seen any degradation of the material. We have then done some on-site stress analysis, measurement analysis, because client requested for further analysis like computational analysis to find out remnant life assessment, which Rob will present in his subsequent slide. And what we have done is we have installed strain gauges at different location of this asset, and we have collected data for 1 month in XYZ direction, and we have seen what is the strain imparted on the structure due to seawater condition. The cutout sample, which we are showing to show in the next slide, we have done macro and micro observation. Again, there was no anomaly in the microstructure found, but we observed presence of pit. And we have done further analysis in electron microscope, which shows presence of pit, and we have done EBS analysis, which shows presence of chlorine. This confirms seawater pitting corrosion on the pipe. Overall, analysis suggested that material has undergone pitting corrosion likely to the exposure to the chlorinated environment. We have done another further analysis of the area where we found through thickness crack and during UD inspection. So this section, when we cut and we do polish, we have seen a crack has generated at the pit location due to environmental condition of the asset. Once again, there was no problem with the material degradation. The whatever corrosion happened is due to pit, and this has also generated crack inside the material. In summary, what we have seen is on-site inspection revealed corrosion under pipe support, and this is due to seawater condition. Notably, the state-of-the-art visual laser camera inspection done by Abyss has reduced the time of inspection a lot. Laboratory examination confirmed the presence of pit, and further analysis confirmed that pit has generated crack inside the material. We have also collected data for stress, which was further used by Rob team for analysis. This analysis data, including dynamic stress analysis data, serve as a valuable input for computation and analysis, which will be now presented by Rob. Rob, over to you.
Thank you, Basab. So it was really nice to work on this project, because as a structural engineer and analyst, it always really pleases me when we have access to such a wealth of information regarding the damage profiles, the materials, behaviour, the damage morphology, local stresses, and so on. So this makes my job a great deal easier, and we can try and employ the tools to get the most accurate representation of actually what the local response is and how this local damaged area will behave over time. So this is really good. What all this data allows us to do is really leverage the use of really accurate simulation techniques, such as finite element analysis, that can be used to support fitness for service type assessments. So fitness for service type assessments are often carried out in a very standardized way, often without numerical simulation to support, but often based on sort of hand calculations, very pessimistic representations of a structure, its behavior, its response to loading, its materials resistances to particular types of damage. So actually having access to all this data and also putting that into partnership with numerical simulation allows us to very accurately say where these areas of damage will be a threat to the integrity of the pipework. Yeah. So that's what we did on this in this case, and this really allows us to very cost effectively manage what's going on in the asset. We can make good recommendations and make good reasonable recommendations as to how the inspection schedule should be optimized, such that there isn't sort of a level of downtime in the plant expensive to maintain. So just getting into a bit more of the detail as to what might feed into one of these types of assessments, and this is the sort of detail that went into our assessment for this case here. We've obviously talked a great deal, and Hamza's brought up all of the very detailed scanning data that can be obtained, the localized morphology of the damage. We can very accurately have those corrosion maps and the pitting maps and the local inspection of those areas of pitted regions identified by Basab with the local crack-like features, and we can take all of that into account. We can take those corrosion maps, areas of generalized corrosion, areas of localized corrosion with the pitting, and also take into account the very specific morphology of the crack-like features, and feed that all into our simulation, which is what we did here. In terms of the testing that was done, that Basab has referenced, and we can bring that forward and convert that into suitable mechanical properties, tensile properties that can give us some feel for how the material might behave in an elastic plastic nature under a given series of load cases. And those load cases will be a function of the internal pressures, the local stresses that are being seen as a result of the response to the attached components, the supports, attached pipework, and so on. So what we were able to do by applying the typical design loads that we would expect for this plant, but also taking into account the stresses that Basab was able to identify as local stresses during the operation, we can validate what's actually going on in the pipework using those stresses that were found, and make decisions as to how we should load the pipework in our simulations to be able to feed into an accurate fitness for service assessment. So modeling corrosion under pipework, it supports is really complicated. It's not something that can be done with a standardized sort of hand calculations in the procedures. We really need to take advantage of numerical simulation, especially when we get very detailed damage morphologies in terms of corrosion loss and cracking, because that's just not something that can be accurately ascertained through hand calculations. So we're able to bring all that damage morphology, a good validated representative approach to what loading conditions are actually being seen through operational conditions, and simulate what the response of the component was to those loads. So that actually tells us a great deal about whether or not those areas of damage that have been seen are safe to remain in place, perhaps until a more convenient time for a shutdown, such that we can minimize the amount of maintenance, the amount of shutdown time on the plant. So as I've mentioned, the typical fitness for service procedures, such as in APR 579, which is one of the sort of highly recognized standardized international procedures for fitness for service, would require that numerical simulation is carried out for complex configurations such as this, where you've got complex geometries like areas of damage sitting underneath pipe supports, where there are stress concentrations, you've got complicated regions of damage and so on. So these, what I term level 3 type procedures, are really useful in this type of analysis that we carried out. And we can also take advantage of the fact that we can actually assess and model simultaneously areas of corrosion, pitting, and crack-like features, so that we can identify what the sort of simultaneous effect that they're having on one another is in terms of their crack driving forces, and compare those to the relevant materials resistances, whether that be a sort of function of the tensile properties, or whether it be a fracture toughness type property. John? And so we were able in this case to demonstrate that the pitting corrosion, the localized corrosion, and the crack-like features that were found were not actually immediately threatening the integrity of the pipework. We were able to demonstrate that, given an assumption of a level of damage propagation over time, those areas of damage would start to become a threat over time. Through fracture mechanics types assessments in the fitness for service procedures, through iterations on our numerical simulations to see what the effects on the global response of the pipework was to increased levels of corrosion and cracking. We were able to identify what the driving forces of those damages were, and also compare them to the resistance of the material and the structure to be able to withstand those areas of damage. And on the right here, I've just got this is not the actual case that we had in the project. I couldn't share that, unfortunately, for sensitivity reasons, but there were areas of damage that were able to demonstrate that they were sitting in the sort of the more benign region of a risk matrix at the point at which they were found. So they had a very low likelihood of causing a failure. As time progressed over the next 10 years, we were able to demonstrate that they were actually creeping into slightly higher severity regions of the risk matrix in terms of the likelihood of failure. So this is because as the damage grew bigger, the driving force to approach the allowables in terms of the as compared to the materials resistance. So it was really valuable to have this kind of risk-based approach to managing the asset for our client, because then they were able to prioritize which of the areas of damage that have been found were going to be the ones that were most likely to cause a failure in future, and prioritize asset management on that basis. So this type of approach is used widely as part of the API 580, 581 risk-based assessment methodologies, in conjunction with the fitness for service methodologies of 579 and others, supported by numerical simulation. And working all together allows us to put together a very robust asset integrity management framework for our clients, like we did in this case. Thanks, John.
That's great. Thank you, Hamza, Basab, and Rob. I guess we just need to summarize some of that a little bit and get into the question and answer. So hopefully that was of interest. I mean, just to summarize, we formed a partnership that we believe adds a lot of value in terms of what we're doing. the autonomous inspections really speed up the inspection process and produce accurate, well-documented records, which I think improve the quality of this type of approach. That allows our colleagues in Singapore to quickly focus on key areas of inspection, any materials testing requirements that spring out of that, which can be done back in the laboratory. And all of this data can be used to really help the likes of Rob with their modelling, simulation, and any other work that they need to do to support a fitness for service assessment. I think the value proposition from this is really summarised in those bullet points. But I think that's it really from us. I mean, it's a valuable process, and I think it's going to speed up this type of approach and reduce the amount of disruption and the amount of cost, and allow owner operators to get back to operation as quickly as possible. Just one last thing to say before we get into question and answer. Codes and standards, very important in this area, in every stage of this. We still rely on the same codes and standards to complete this type of work. And whilst we've changed the approach a little bit and sped things up and everything, we don't need to make any changes to the regulatory environment in order to continue, in order to introduce these methods. So we're confident that what we're doing is with modern codes and standards, and there's it's not necessary to actually change the environment that we're working in. Just plow on with this. So I think that's it from us. I think it's over to the audience for question and answers. Now I think Stan and the team potentially have been collating some questions for us. I don't know if we can see them. We have the first question in from Alson Hafiz, is it? For cups inspection, what would be the best recommended practice for inspection as per code? Are you happy to pick that up, Hamza?
Yeah. So as far as code inspections are concerned, with regards to cups, what we've seen are two types of industry practices. One is the methods which require the pipe to be lifted before it can be inspected, and certain methods that can only be done while the pipe is in its original place. So in order to get the right information and reduce the downtime of the facility, we've always seen the best output coming from a combination of these methods. So if an initial assessment is being done while the pipe is in place, which let's say in this case was an AI-based visual inspection, or if you would like to do some other form of fixed sensor installation or some sort of guided wave technique while the pipe is in place, that is something that is being used in the industry. And if you have the capacity to lift the pipe for just a preliminary inspection, then of course you've got many other methods that you can take into account as per code recommendations. So you've got guided wave, you've got phased array, you've got your conventional UT in that case. But while the pipe is in its place, there are very few techniques that could practically be applied here. And I think maybe Basab can comment further on this.
Yeah, I mean, further to that, there are also long-range UT people use for this type of inspection, but I don't know how. I mean, it's not very successful, or I would say it works in certain cases only. There still work going on. Thank you, Hamza.
Hey, thanks, guys. Another question on the inspection side of things. I think it's from Kenneth Brian Gomez at McDermott. I presume this technology can be applied on offshore platforms, but is there a way to apply this technology for offshore pipes? I think we might have something there, Hamza.
I think we need a bit of clarification on the question. Are we talking about offshore underwater subsea pipelines? If yes, there are systems in place that Abyss has and are available in the industry as well, which can be used to capture similar forms of high quality data but for underwater or subsea pipelines. So yes, the data capture stage kind of changes a bit, but once we get the high quality data, we can then repeat the assessment as we have done for offshore topsides. So I hope that is the answer to your question, Kenneth. If not, you could probably add a follow-up question. Yeah, go ahead, John.
I'm just looking through the questions. I've clicked on the same one 3 times, so I'm trying to find a new question. A lot of these questions are related, so I'm just trying to find new ones. Actually, Kenneth has clarified. He said offshore sea underwater pipes, I think. So let's keep going. Can we get a copy of the presentation? Has come up a number of times. Yes, we can. The presentation has been recorded and a link will be distributed after the presentation. Here's a question. What's the main difference between cups and crevice corrosion? That comes from Ganesh PM or PM Ganesh. What's the main difference between cups and crevice corrosion?
Well, one happens under insulation, another happens, in a condition where you can be a nut and bolt, you tie it together, it can happen. Both happens due to chlorine, but it's different location, so different type of mechanism.
Thanks, Basab. A question here from Arslan Hafiz. What should be the best insulator or barrier between the pipe and pipe support to avoid corrosion other than using coatings?
Yeah, so in the industry, we've seen a bunch of different options, but uh, in this example, even if you remember the slides, there was an additional barrier already installed between the actual support and the pipe. However, the damage were still progressing. So it really depends on the severity of the environment, especially offshore, what you're looking at. But there's a bunch of these different branded um, types of spacers that you can add underneath the pipe and in between the pipe support. So there's a bunch of these available. There's I-type spacers, which essentially allow moisture to fall off the support as it kind of collects there. But as you can observe in this case study, we had those sorts of mitigations already installed, but the severity of the environment was enough to still cause a propagation in the damage, and that is something that needs to be analyzed in a bit of detail before we can go to mitigation. So yeah, there's a bunch of I can't name a few of these industry available brands that are out there, but there are a bunch of these barriers that you can install underneath the pipe.
Coming back to earlier, I think at the start of the presentation there was a hand or two going up. I think Shahab Uddin, and I do apologise if I'm mispronouncing people's names here. I'm doing my best. But Shahab had put his hand up a couple of times. I think he's put a question in around about the API standards, and in particular, he's interested in whether or not they can be applied on steel structures. And if not, then what can we best use for offshore and onshore steel structures? I think I know the answers to that one, but I'm gonna ask Rob to answer that one. You're quite familiar with the API standards.
I'm guessing if Shahab is referring to the fitness for service standards, the API fitness for service standards, then yes, the API 579 procedure was originally designed to allow assessment of pressurized steel components, whether those be pressure vessels, piping, pipework, tanks. So certainly they can be applied for onshore, offshore structures as necessary. It's a standardized approach that really requires you to understand what component you've got, what damage morphology you've got, what the materials resistances are, and what loads the component is seeing. So it's quite agnostic in that way. So really, yes, it is designed for steel pressurized components. I hope that
Yeah, I
answered
think
your
that
question that you were actually asking.
I think that does. I think it does answer the question, because there's another message come up from Shahab, which is please organise a webinar for offshore and onshore seal structure inspection. So I think well, that's a good idea. I think we'll follow up on that. Thank you. I'm just looking through the questions. Luke, have you seen any questions that are different?
Yeah, there's a nice one from Mohammed here. Just right at the top. So what's the AI limitation of detecting defects in this scenario? I think that's a question for you, Hamza.
Yeah. Could you repeat the question, Luke? What is the
So
area limit?
what are the limitations of using AI in detecting defects in this scenario?
Yeah, very good question. So there's a bunch of limitations in terms of coverage, what we refer to as coverage. But we've seen quite a bit of benefit when we compare it to traditional methods. So when you are capturing the data for the AI assessment, if the data is not up to a certain standard in terms of quality, as well as if the data is not collected to a certain sufficiency, for example, if you've got a 5,000 square meter facility and it requires 1,000 data points to be collected and you collect only 800, that leads to a limited coverage in terms of what the AI can detect. So that comes from the data capture side of things. When it comes to the analysis itself, we have tested this technology across multiple regions, multiple types of plants and facilities. And what we've seen is that this type of system that we've implemented has a 90% accuracy in terms of detecting and classifying corrosion. So what that means essentially is that 90% of the time, if the system is able to identify a point of damage and then classify it as severe or moderate or whatever, then it will be accurate whenever you verify that, or if you want to verify that through an EMPP certified or API certified individual. Now, the 10%, how we mitigate that limitation of that 10% is, and it typically comes from areas which are very, very dark, dark corners, areas which may be blurred out during the data capture, or small locations which are not very accessible, even if a human was to go there. So these indications are basically flagged by the system. So it still highlights it as something to look at instead of saying it's severe or moderate or heavy, so that we can target those instances individually as opposed to um, leaving them completely untouched. So it's a 90% accurate system. We've tested it, verified it, and the 10% we try to manage through flagging of those points so that a inspector could go in and verify 10% of those locations. So I hope that covers what you were thinking about the limitations. Other than that, we haven't come across any major limitation in terms of external visual inspections.
I think we've got another question here from Richard Ashley Smith, who is based out in Bristol. I wonder if you're related to another Ashley Smith that we know. Can you provide detail, or a little more detail, on how the data capture is conducted? How resilient are the capture devices, and are there drone compatible options? I think we'll give some quick answers here, but I think it's probably worth a follow-up call or a conversation, Richard, to potentially give you a bit more detail on that. But I don't know if there's anything you want to add to that, or potentially answer the question right now, Hamza, in terms of drone compatible devices and that type of stuff.
Sorry, is that drone devices?
Yeah, so just a little bit more detail on how the capture is conducted, how resilient the capture devices are, and are there
Yeah.
drone compatible options?
Yeah. Very good question. So currently, the most optimal method, which leads to this 90% accuracy that we're talking about, has been the ground level handheld laser scanning devices. So the one that was showed in the slide, or a couple of other models, these are all available in the market. So these are handheld devices, usually mounted on a tripod, and you could carry them onto different locations across the facility. Now, this has been the most appropriate method in terms of accuracy as well as time to capture the data. However, the same activity can be conducted through drones. However, when we use drone systems, there is a typical limitation on the payload of most industrial drones that are available in the market. So what that means is the drone sensing system actually is different from this handheld system. So a key limitation that we see is not necessarily in the detection of damage, but in the classification of damage when you have drone captured images. Plus, there's the fact that most of drone payloads available in the market um, do not have laser scanners pre-built into them. If you have a LiDAR scanner, that's great. However, these LiDAR scanners are much low resolution as opposed to this handheld devices. So we then lose out in some of the accuracy, we lose out in the quantification of the damage, which Rob's team is definitely it's very useful input for their finite element analysis. So we have to sacrifice a bunch of things if we want to include drones in the capture, but definitely we have done drone capture before, and it is possible.
Thank you. I've got a question from Sunil at Element, which I think is probably one for you, Rob. What are the best software options available in the market for remnant life assessment and fitness for service?
Right. Yes. There are a range of software options out there. Unfortunately, most of them are tailored towards sort of codifying the sort of basic hand calculations that are in the fitness for service procedures. So the basic ones where you've got a very simple damage and a simple pipe structure and identifying what the integrity of that is. So it's often easy to sort of build your own sort of spreadsheets sometimes, or MathCAD sheets for these types of things. But there are software solutions out there, and I'm sure you advantages and disadvantages in terms of what we've talked about today. There are no bespoke software solutions that deal with where you need to assess a complex geometry, bespoke material properties, and so on, simultaneous different regions of damage all interacting with one another, and so on. So in these cases, it's always best to conduct the numerical simulations and exercise some expert engineering judgment as to what the data is telling us, what the simulations are telling us, which is something really that codified software solutions wouldn't be able to do, really. So I would always say exercising engineering judgment at this stage is always one of the most important aspects of this type of analysis, which isn't something that can be codified yet. I'm sure AI will take over my job in the coming decades, but it's not there yet.
Thanks, Rob. I think just to be fair and spread the questions out a little bit, we've got a question here potentially for Basab in the materials testing lab. It's come from Arslan at SSG. Kindly share the equipment name which detects the tensile strength of the material without destroying or destructing the sample. I don't know if you've got any thoughts on that, Basab.
There is none, to be honest. What people do for carbon steel mainly, they go to site and take hardness, and there is a simple conversion from hardness to tensile, which is completely empirical, and you have to first convert the on-site hardness measured by LEAP or UCI to the HV or HV Vickers, and then you convert that to tensile. This is totally empirical. There is no equipment or no standard agreed formula or equipment there who can do tensile test without destroying the material.
That's right. That is the correct answer, Basab. But I wonder if Alzan is referring to some equipment that Element's been investing in out of the Cambridge area. It's the James Dean invention, isn't it? Which is a plastometer. And you know, we're going great guns with that. There's a portable device available now. We'll follow up with you, Azan, about the plastometer and potentially put you in touch with that team if that's something that's of interest. I think we've got your email address here, so we can get in touch and follow through with some information about that device. But that's not something that's a standard device that's being used in our laboratories right now. We are invested in it. We are helping to develop that technology, but it's not something which has got through the various codes and standards that is available to this type of thing right now. But it is showing a lot of promise, and people are starting to use it in deregulated industries. But aerospace, oil and gas, energy, you know, I mentioned earlier, there's a whole lot of codes and standards that we need to stick with. So technology's coming through. We're working on it. Hopefully, we'll have that with you shortly.
Yeah, thanks, John. I have a quick question for Rob. So through your modeling and simulation, are you able to develop a comparison for the effectiveness of different repairs? Is that something that you can do through your software?
Yeah, I think if there was situations where damage was found to be unacceptable, we've got the tool sets available, and we have done very recently investigate situations where proposed repair solutions that we need to understand sort of what thickness of patch repair we might say want to put over an area of corrosion, so we can try to optimize that solution by understanding how big the patch needs to be, how thick the plate needs to be, where it needs to be connected, and so on. And we can very quickly optimize that solution through some iterative numerical simulation. And like quite recently, there's all sorts of different options, all sorts of different repairs for different scenarios, but that is certainly something that we do and we have done very recently.
Yeah.
Okay, any more, Luke?
No, I'm just having a look now.
There's a
We've got a
question again from
question.
Arslan.
Yeah.
How do we detect corrosion under pipe supports for insulated pipelines?
Yeah, that is also a good question. So for insulated systems, there is a key limitation that direct visual inspection is only possible if you remove the insulation barrier. So that is an industry-wide problem. However, corrosion under pipe supports specifically when we are targeting and we know that this is the type of issue that we're facing, and there are insulated systems available. So this AI-based technique actually allows us to, number one, segment between insulated systems and non-insulated systems. So you get a list of, you can segment the visual data into these two parts. Within the insulated systems, we are then able to, instead of looking at direct corrosion, we are able to automatically detect and classify instances of jacketing damage. So if the outside jacketing of an insulation shows signs of damage, for example, if there's a puncture or there's a stain or there's water dripping and it kind of leaves a mark on the insulation barrier, combining that with the fact that there's a support present in the vicinity. So that combination of logic essentially leads us to a method of indirectly trying to catch these instances. So you've got insulated items filtered out, you've got your pipe supports already identified, and then any sort of indication with respect to damage of the external jacketing of insulation is then detected by the system, and then we prioritize based on that. So yes, there are limitations because it's not a direct visual inspection. You have to remove insulation for that, but we are still able to cover these instances and create a report that that can be actioned upon in a step-by-step and prioritized way, as opposed to just ripping off insulation from every single pipe that you see.
Thanks, Hamza. I think we're getting to the end of the session. So there's probably not many more questions left. There is one question that's coming from Mohammed that I'd like to answer. It says, can we get a dummy full case report to help us get a hand on this? That's a really good question. So I mean, obviously the presentation takes you through the process and a little bit of detail in terms of how we get from inspection through to full fitness for service report, if you like. We're obviously not able to give you our client reports and send you that information, but I do think we've got enough here that we could potentially put a paper together. So I think if we get a short paper potentially that summarises all of this in writing, then maybe that is something that we can use as a dummy report, if you like. So I like the question. I think it's a good suggestion. So thanks for that one, Mohammed. I think in terms of just wrapping up then, there probably are a number of questions that we haven't got to. We promise we'll get back to you. We will get back to everybody with answers. Please get in touch if you've got any more questions after the session. And thank you very much. Thank you to the speakers. Thank you for Luke for being on hand with the question session. And thank you for everyone for attending, and especially for some of the questions. I think they've given us food for thought, and certainly will help us improve the way we're doing things. So, thank you.
Thank you, everyone.